Okay, good afternoon. It's time to start. So I have uploaded the homework on the reinforcement learning with human feedback, and it will be the easiest homework because you will just need to run the code and train reward model and just apply this model later on results of large language model. So I think, yeah, you can do this maybe in half an hour. So last time we talked about optimization of language models with structural transformations like distillation, using smaller models, or pruning. Today we will talk about another approach to compress the weights of the layers of language models. So if you think about the standard precision 32 bits, so do you remember what does it mean? What does it mean range, precision, how the numbers are stored in float format? So for example, if we have 1.5 e negative or e plus 5. What is that? So for example, negative 1.5. Or I think you can write also negative 2 e and then, for example, plus 5. So what does it mean? I mean, how it's stored in which part is precision and which part of the number is range. So the first bit, it's sign. So yeah, we don't need to think about the first bit. What does the range represents 5? Is it range or precision? We don't.
I think the 5 is.
What?
I think the 5 is range.
Yes. So in float 32, we have 8 bits for the exponent and 3 bits for the number itself, for the significant digits. And in scientific notation, it it will store about 9 digits, but in neural networks, if we use random noise, for example, or drop out, maybe we don't want to store all 9 digits after the dot. So maybe we can keep only 3 digits. So this is one idea. The second idea, typically, the weights of neural network are not very large. So maybe we don't want to have Um, so 2 bits, it's 10 power, 2 power, in this power 258. So maybe we don't have so large weights in neural networks. Typically, they uh, no larger than hundreds. I don't know, maybe thousands would be enough. So that's why we can use a smaller precision data type, and it will help us to use the memory more efficiently. So do you remember which weights are, which layers in large language models, in transformer models, um, which layers take more space? So we have layer norm, we have activations, we have linear layers, and that's it. So which layers use more storage? Linear, yeah, because uh, to go through dimension, for example, 8,000 to 8,000, we will need to store a matrix 8,000 times 8,000. So typically, when we compress the weights, we compress only the W matrix and we don't compress bias terms, because biases, they use much smaller uh, storage than weights. So the other format is float 16. In float 16, so this is the standard precision for training neural networks in all frameworks, including. Oh, by the way, David, you were right last time when we were talking about GPUs. Yes, Collab provides for free GPU cards, not the CPU card. So uh, yeah, I remembered about this because so standard GPUs work with float 16, but there is another format, uh, bfloat 16, which stands for brain flow. I don't know why they use this word brain and use everywhere. So what is the difference between B float 16 and just float 16? And the TPUs, they use B float 16. You don't know. So the difference is that in float 16, we use 5 bits for the range for exponent. In bit float 16, they use 8 bits. And how many bits then we will have for the precision? For the Yes, 7, because 1 is for side, 7. And if we use 8 here, then it will be easier to convert from float 32 to float B16, because we won't we won't go kind of outside of the range. Um, and uh, let's look at the example. So, for example, uh, NumPy doesn't have B float 16. NumPy works only with float 16. But Torch, it has, so let's import Torch. And for example, I will create a tensor. So this is a famous example, uh, uh, like, which is called go over 300. So let's create a torch tensor 300 and use 16 float 16 data type. And multiply by the same number. Hmm. And we will get overflow. Why do we have overflow? So if you look at the range, so 5 bits, and here we will have, so it's a little bit, it's not 10 power 5 because it's actually 2 power 5 in machine representation of numbers. Uh, we write e plus 5. We mean the multiplication by 10 power 5, but in real representation, it's in binary system and it's 2 power 5. So that's why the result, which is 300 times 300, will just go outside of the range. But if we use B float, then it will work. Hmm. It's interesting that it returns some uh, kind of non-relevant digits. Um, so if you want to reduce the storage more efficiently, you can use float 8. Mm, so this is int, but there's also float 8. And then you should to decide how many bits you should use for range and how many for precision. But there is no much choices because the first bits you will use for sign, so you will have just 7 bits left, and there are data types E5 M 3 sorry, M2 to match 7. It means that they use 3 bits for range and 2 for precision. It's also called mantissa. Or E4 M3 and so on. And we will use um, integer int 8 for one of the algorithms of quantization. So what is the range of int 8? Or maybe let's look at the easy question. So assume we have a layer of neural network with some weights, and weights have some distribution. Like we have some weights around 40, around 20, and we want to convert, for example, in int 4. What is the range of int 4? What is the smallest and largest number? Yes.
Is it -8 to 7?
Yeah, typically it's -7 to 8. Yes, yes, correct. So how to convert these numbers into range between -7 and 8? Yeah, because these numbers are outside of the range, actually. The idea is to scale. So you can shift these values by some number z, and also divide by the range max minus mean over the maximum range of your data type. So this is the transform that you can use. And clip to fit the range. And then you can use the inverse transform to reconstruct these numbers in range of int 4 to the float 16, for example, or int 16. So another idea is to take into consideration the distribution of these weights. Like instead of using the even spacing, we can maybe use quantiles. Quantiles are the inverse of CDF, of the cumulative distribution function, and use these quantiles as the values for our data. Yeah, so there are different approaches. You can use also k-means for clustering. Another approach is to cluster the groups of the components. For example, use the first and the second coordinate and find the centroid only for first coordinates. For example, for one group, like first and second. Find another centroid for third and fourth, for example, coordinates, and it is used in retrieval models that we will talk about next week. It works pretty well, but because it compresses pretty heavily the data, it doesn't result in a good precision. In retrieval, we don't want to have very high precision, but for neural networks, it doesn't work well. There are different algorithms, so like orthogonal product quantization that quantizes kind of groups of the coordinates. Um, okay, another algorithm is to look at the most important weights and quantize only that weights, for example, in 8-bit, and don't quantize, oh, sorry, and leave untouched these important weights and quantize just not important weights. So another approach of quantization method is called NF4, nearest float 4. Oh, sorry, normal float 4. No, the method is called um, RTN, round to nearest, but NF4 stands for normal float 4. So instead of using the even distribution or learn sum distribution from the weights, we can use a standard approach. Okay, let's assume that our weights have normal distribution and use the quantiles of the normal distribution as to convert our data. And this, so we have 7 numbers to the left and 8 numbers to the right for int8 precision, and we can convert these float numbers into integers, just assigning the index of each number. And this method you were using in your homeworks when you load in 4-bit precision, then it quantizes using this format NF4 on the fly. And then you can also reconstruct back. The question is which precision we should use when we want to quantize models, and the answer is 4. So here are some plots. These are models that from Facebook that were before Llama, OPC, and here is the number of parameters in the model and different precision. So, for example, if you want to compress to 3 bits, then you can see that the accuracy of the model, even of large model, is compared with accuracy of smaller model, but quantized with high precision. So maybe you don't want to quantize 170 billion parameters model to 2-bit precision. Maybe it's better to use 7B model and quantize to 8-bit, for example. But in papers with high compression, where they quantize, for example, if you use this approach, you can, for example, cluster 2 coordinates to 1 coordinate. So you can, for example, quantize a vector, a number with 16 bit precision to 8-bit precision, and it means that every number will use half of bit kind of precision, because if you group two features together and store in 8-bit precision, and originally they used 16-bit precision, then you kind of use half a bit for every feature. So if you hear about 1.5 bit quantization, so this is what people actually mean by that. So yes, in the papers that propose very low bit quantization, typically they don't compare with smaller models. They just compare with large models, and but if they try to use smaller model and use high precision quantization, the performance will be maybe even better. Okay, so this is our goal: to make models faster, to make models smaller, and the approaches that we talked about are quantization, pruning, and maybe factorization if we use matrix decomposition. And there are three situations: when we have data and when we don't have data. So if you don't have training data, then you should use this in F4 quantization. Just fixed mapping between floats and integers. But if you have some data, well, if you have training data, you can even train model, quantize model. But typically, people don't train quantized models because then you want to use these models with different precision. And if you train your model with low precision, then it's hard to reconstruct, for example, to a 16-bit or compress. So typically, the models are trained in B float 16 precision, and then you can quantize to smaller precision. But if you want to compress models during training, then in practice you can quantize one layer and train the model with this layer frozen. So you will train other layers. Then after several epochs, you can quantize next layer and freeze that layer. So sequentially, incrementally, you can train your model with quantization. So, but if you have just some data, then there is another idea how to use this small amount of data to compress the model more efficiently than just using the normal float quantization. Okay, this is just overview of the methods: quantization at training and quantization post-training. So, as I said, we will actually work with post-training quantization because it's mostly used in practice. Yeah, this is how we can train quantize during training. So, you remember last time we talked about optimal brain damage. So, the idea of quantization also uh, takes roots in this algorithm, optimal brain damage. So, it was proposed in late 90s or late 80s in 1989. And um, the guys who took my machine learning class, they know that I'm very skeptical about connections between neural science and machine learning. But you will hear every time neurons, brain. Okay, so let's look at this algorithm. Um, optimal brain damage. So at that time, neural networks were very small, and they could get the loss function almost to zero. So if you have optimized your function, then what is the gradient at the minimum? Zero. So if you use Taylor expansion, then you will have the value at the optimum plus the first order terms, which is zero, and then the second order terms. So this is the second order term, like delta of weight. And for the first order term, we have gradient. For the second order term, we have Hessian, which is the matrix of second derivatives. So the idea of this algorithm was as follows. So if we have some loss function, of course, it's multidimensional. So the shape looks like maybe paraboloid. We can try to approximate the minimum with parabola, with a squared function. And that's why if we use only second order term from our loss function, then we will get this shape. So this is the shape of the complete loss function, and this is the shape of the truncated loss function. So which neurons we can actually remove from our brain from neural network? Let's try to remove some neurons such that the resulted loss function is very close to this parabola. So, for example, just by grid search, we can remove one neuron and calculate the loss function. up to the second order. And we will get a little bit lower dimensional paraboloid, but it still will have the shape of paraboloid. And we will look at the difference between minimum of original loss function and loss function with some removed weights. And we'll remove, for example, we want to remove 8 or 10% of weights. So we will choose this 10% of weights such that the loss function is as close as possible to the original one. So this is the idea from this paper. The second idea is called optimal brain surgeon. So the next paper is called optimal brain surgeon. Again, from early 90s. In this paper, instead of just removing damaging brain, they propose to sew in the damaged neurons. So that's why it's called optimal brain surgeon. So the idea here was I don't see the. So again, the same loss function, again, the expansion up to the second order, but when we remove one neuron, so for example, we had the approximation of loss function, and after removing one neuron, the loss function not only changed the height, but also shifted a little bit. So let's remove one neuron and then update other weights such that the new loss function will be shifted to the position of the original loss function. Then we will remove another neuron and update the other. For example, if you think about okay, now let's talk about quantization. So this paper is called optimal brain compression. So optimal brain compression. And you can see this paper from 2022, 30 years after the optimal brain surgeon and damage papers. So in case of quantization, instead of removing weight, you can think about quantizing one column of your matrix of the weights and update other weights to make the loss function closer to the original one. Then quantize next column of weights and update the remaining. For example, if we have 8,000 parameters, we update one column and then we quantize one column and then we update remaining 7 999 parameters, and so on. So it's just iterative process, and for loop will go from 1 to the total number of parameters. So, but to get this Hessian, the matrix of second derivatives, you should also then invert this matrix. And of course, if you have several billion of parameters, what will be the shape of the matrix? It will be this, let's say 7 billion times 7 billion. And it's impossible to invert. So the idea of this paper, optimal brain compression, is instead of using the entire model to compress only one layer at a time. So let's say again, this method assumes that we have some training data. So X is the matrix with our training data. As you remember, it has data in rows. And W are weights of our layer. So they propose to apply the optimal brain surgeon idea not to the entire model, but to one layer. So if we have one layer, what will be the shape of this Hessian? Because it's a squared function, and you want to minimize. So this is the matrix with original weights, and this is the matrix with quantized weights. Let's say we use only the first feature, then it means we will quantize only the first column of our matrix of weights. So the Hessian will be X transpose times X. Because if you want to minimize this squared function, then you will have the second order term, W transpose times X transpose times X times W. And if you take the derivative, then you will get this second derivative, W will go away, and you will have only X transpose times X. So what is the shape of this matrix? The number of rows, what is the number of rows in training data? Is it the input size of our layer, or it's the number of data points? It's number of data. In rows, we have data times the second dimension will be the number of features or inputs in our layer. And as the result of the product, instead, we will have matrix I by I, number of inputs to our layer. And if the dimension of our layer is, let's say, 700, then it will be matrix 700 by 700, which is better than 7 billion by 7 billion. And then you can just solve this minimization problem analytically. So the algorithm is as follows. You quantize the first column of the matrix and solve this minimization problem, where W hat is the matrix with first column quantized. Then you quantize second column, and you don't touch the first one anymore. And again, solve this problem. And repeat this the same number of times as the number of features. And this algorithm I think you remember, it's called PTQ. In one of the notebooks, I uploaded models with on the fly quantization, but also I downloaded the quantized model, and the model had name Llama PTQ. So it means that it was quantized with this algorithm. Uh, so yes, if you want to have better quantization, then you can um, quantize your model with some training data. Okay. Yes, so these are these papers. Hmm. And we will actually implement this algorithm in our, so we will start this next time, and you will continue in homework. And there are other approaches like sparse GPT, the same idea. You can drop some neurons from the first column, solve minimization problem for matrix, then drop some neurons from the second column. So the same idea, but instead of quantization, they drop some neurons. And many other algorithms, which, if I remember, AWQ, for example, it also quantizes the activations, because in PT, in GPTQ, we don't quantize biases and activations. Okay, so this is the end of the theory, and next time we will do code in practice and quantize numbers in 16 float 16 to 8 or 4 int.